Hello, I am David Salzberg, the chair of the Department of Physics and Astronomy. Thank you all for coming today to the annual UCLA Saxon Lecture. This is our department's main event of the year. The Saxon Lecture has been held annually for over 30 years. More than half of our speakers have been Nobel laureates. And today, for the first time, we have one of our own. So Professor and Nobel laureate Andrea Ghez is the Lauren B. Leichman and Arthur E. Levine Professor of Astrophysics and will be speaking today. Thank you, Lauren and Arthur, for so much support to Andrea and the Galactic Center Group over the years, starting with when she was junior faculty. And I also extend a thank you to the Prestons, Howard and Astrid, who have supported Andrea as well as many other aspects of the department. And I am pleased to make the announcement that the Prestons are supporting a complete renovation of the UCLA Remote Observing Room located in Knudsen Hall. And thank you also to the department's other special supporters, some of whom are in the audience today. Now, this year is also special because the following of David Saxon's children are here today. Barbara, Linda, Charlotte, and Victoria, and many of their spouses are here. And we are delighted to also have David's grandson, John, who we're happy to hear is majoring in physics. Well done. David Saxon was a giant of physics, the University of California, and our department. And now Professor Emeritus Ned Wright will tell us more about Professor Saxon.
Hello, I'm Ned Wright. And it's my pleasure to introduce this Saxon lecture by my office neighbor, Nobel Prize-winning Professor Andrea Ghez. As a previous holder of the David Saxon Presidential Chair, I've been asked to say a few words about the namesake of this series. Like Andrea Ghez, David Saxon started his college education at MIT and ended up at UCLA. I myself was teaching at MIT before moving to UCLA, so the MIT to UCLA physics path is a well-traveled one. David Saxon finished college as World War II was heating up in Europe. He finished his PhD at MIT at the height of US participation in the war. He went to work at the radiation lab at MIT. The radiation studied at the RAD lab was microwave energy for radar and not nuclear radiation, even though David Saxon was a distinguished nuclear theorist. But remember that while the war was ended by the atomic bomb, the war was won by radar. As an aside, my dad also worked at the RAD lab during World War II, and I worked with Ray Weiss on the Cosmic Background Explorer in Building 20, aka the Plywood Palace, that housed the RAD lab during the war. David Saxon came to UCLA in 1947 as an assistant professor and left in 1983 as president of the entire University of California. But there was one bump on the road. He was fired in 1950 for refusing to sign a loyalty oath during the Red Scare. While president, Saxon made an important decision to go ahead with the 10-meter segmented telescope in Hawaii, now the Keck Observatory. This facility has been essential in Andrea Gez's Nobel Prize-winning studies of the Galactic Center. Saxon then returned to MIT as president of their corporation. But finally, he retired again to do what he loved, and as I remember him, an emeritus professor at UCLA, attending many seminars and colloquia, and always curious, and always asking the best questions.
Thank you, Ned. And now, Professor Emeritus and Associate Dean Ferd will introduce Professor Ghez.
Well, Andrea came to UCLA uh, in response to a faculty position offer, or faculty position that was opened up, and Professor Mark Morris, who was chair of the Department of Astronomy at that time, convinced her to apply for it. When she came, there were a couple of things that happened. She had lunch with the chair of the physics department, who was Roberto Poche, who flatly informed her that she would never be hired at UCLA with only 1 year of postdoctoral experience. Not exactly the most encouraging way to begin a job interview. Then she gave an absolutely spectacular job on her measurements of the binary star systems using speckle interferometry. And it so blew away the astronomers that they overcame the reluctance of the chair of the physics department, and she was hired into a joint assistant professorship. And she took the first 2 years of that professorship on leave in order to complete her Hubble fellowship. But it made her eligible to apply for Keck observing time. The Keck Observatory had just become operational at that point. And so she put in a proposal to do speckle interferometry of the Galactic Center. That proposal was summarily shot down by the Time Assignment Committee with the argument that what she had planned to do was impossible. Well, Andrea is a firm believer in the American way. The difficult she does immediately, the impossible takes a little longer. So she borrowed some observing time, borrowed in the sense of Huckleberry Finn, and made some speckle interferometric measurements of the Galactic Center, reduced them, showed that indeed you could do these observations. And her next proposal, of course, was accepted. And she's been on the game ever since then. In the intervening years, lots happened, but I'd like to just mention two things. One pleasant and one unpleasant. The pleasant one was that Laura Leichman and Arthur Levine took an interest in her research and began to provide some philanthropic support, and ultimately created the chair that David mentioned. And later on, Howard and Ashton Preston have also contributed to that. The philanthropic support for astronomy cannot be overemphasized. Astronomy is a very lean field from the point of view of getting funding for single investigators. And that support makes a tremendous difference in being able to carry out a forefront research program. The unpleasant part of what happened in the next few years is she had a competitor. Reinhard Genzel from Berkeley, but mostly as the director of the Max Planck Institute in Germany, was much less than a collegial colleague to her. Several times browbeating her, and that's the only term I think is appropriate, into trying to publish her results before they were ready for publication. But Andrea stuck to her guns and published only when she was sure that the science was right. Fast forward now to, of course, the events of last October, when they both were jointly named Nobel Prize winners. I understand now that the smoke that surrounds their relationship is coming out of a peace pipe rather than a gun, the barrel of a gun, and that's all to the good. All's well that ends well, as the bard would say. There are two things I'd like to say about the Nobel Prize. The first is that unlike many of UCLA's Nobel Prizes, the work for this prize was done here, so that the institution and her philanthropic supporters can take pleasure and pride in her accomplishment. Second thing is that a research project of the scope of the measurements of the galactic center was not done by one person alone. She had a wonderful and brilliant cadre of graduate students and postdocs who helped her along the way. She nurtured them, she trained them, and in many cases, she sent them off onto excellent future careers. But she always gave them credit for what they had accomplished. Her personal integrity fully equals that of her scientific integrity. So we can't stand up on Zoom, but we can unmute our mute buttons and welcome Professor Andrea Ghez.
Thank you for those very, very kind and generous introductions. It gives me so much pleasure to be giving this lecture today. This lecture, both because it's the Saxon lecture, and Saxon was played such a critical role in enabling the University of California to achieve its dream of having a 10-meter class telescope. And this was an achievement in terms of a system-wide investment that was truly, truly remarkable. I'm delighted to tell the story of how it came about that UCLA really positioned itself in a leadership role with respect to this observatory. So my position, as Ferd alluded to, the history was actually part of what I think was called at the time the merger bribery, the merger between the physics department and the astronomy department. And at the time, Ferd Corniti and Mike Jura really had the vision that they could use this bribery of multiple faculty lines to make a coherent investment in an area that would enable UCLA to play a leadership role in the Keck telescope that was coming online. And this was 30 years ago. So what was recognized 30 years ago is that the technology of infrared astronomy was going to play a huge role. And it was a technology that was evolving very quickly, and a technology driven by the aerospace corporate industry that's located in Los Angeles. So this vision of playing a leadership role in the science, the technology, and the methodology associated with infrared astronomy was truly brilliant, and created a department that has tremendous coherence, collaboration, and synergy. And it's a place where I think we can truly say the whole is greater than the sum of the parts. So I'm very grateful to have had the opportunity to work in this department for the last, 26 years. When I was hired, what I was particularly interested in was working on new ways of using these brand new telescopes. And in particular, developing techniques that would allow these telescopes to overcome the distorting effects of the Earth's atmosphere so that the highest resolution, the sharpest images could be achieved of the universe. And in particular, what I was interested in doing with this technique was asking the question, is there a supermassive black hole at the center of our galaxy? Oh, my apologies, I'm realizing I'm not in presenter view. Okay. And there are two perspectives on why this question is interesting, and this work continues to be interesting. And one, the first is you could think from a fundamental physics perspective. Inherent in that question is the question, do supermassive, and what I mean by supermassive I'll get to in a minute, black holes really exist? And black holes hold a place of particular fascination within the physics community, because while they're anticipated by Einstein's theory of general relativity, so our best ideas of how gravity works, it's also understood that these are objects that represent the breakdown of our understanding of how gravity works, because we don't know how to describe gravity of objects that are infinitesimally small. So in other words, which is what a black hole is. So there's a breakdown in our understanding of how to make the laws of gravity work together with the laws of quantum mechanics, which describe the physics of the very small scale. So that's the drive to understand the possibility of these exotic objects. And then ultimately, this is an object, if we can prove that it's there, that provides an arena to test our understanding of how general relativity works as we approach the region in which perhaps signatures of this breakdown might appear. Now, from a second perspective, what I might call the astronomy perspective or astrophysics perspective, the interest in black holes, and in particular the supermassive black holes, is understanding the role that they play in the formation and evolution of galaxies. And this story is one that has evolved dramatically over the last 2 decades. So even the way we phrase this question has changed over the course of the work. But today we understand that the mass of black holes at the centers of galaxies, these supermassive black holes, appears to correlate very well with the mass of the central component of galaxies known as bulges. That's always about 0.1% of the mass. And what that tells us is that black holes are essential in terms of understanding how these objects form, that they form together, and that there's some cool regulatory mechanism that keeps the growth of the central black hole and the galaxy, the host galaxy, in sync. It's useful to note that galaxies are the fundamental building blocks of the universe. So if we want to understand the evolution of the universe in which we live, understanding the role that black holes play in these fundamental building blocks is important. So these are the two reasons that understanding the possibility and then using this as a laboratory of a supermassive black hole at the center of the galaxy is important. Now, to turn our attention to how one might prove that there's a supermassive black hole at the center of our galaxy, one has to understand what a black hole is. So a black hole is an object whose pull of gravity is so intense that nothing can escape it, not even light. It's also an object who, for which the force of gravity has overcome all other known forces that can oppose the inward force of gravity, forcing the object that's going to become the black hole to become that infinitesimally small object. So it's a singularity because it's mass inside, or you can think of it classically as mass divided by zero volume. Now while the black hole itself has no finite size, there is an important size that you can associate with it, which is the Schwarzschild radius. It's an abstract location in space around the black hole, and it's the last point at which light can escape it. So in other words, we can't get any information from inside this radius, which is also known as the event horizon, simply because you can't gain information from inside that point. It's also the point at which, if you can confine an object to this scale, and every object, with a given mass, has a Schwarzschild radius associated with it, which is just directly proportional to mass, that if you can confine that mass to that scale, that's the point at which gravity is going to win over all other known forces. So the proof of a black hole really resides, direct proof that we're going to go after, is showing that there's a lot of mass inside a very small volume and get as close to this radius as we possibly can. Okay, so now we're talking about supermassive black holes, which are 1 million to 1 billion times the mass of the sun. And I want to distinguish those from what we call the stellar mass black holes. The stellar mass black holes are actually the black holes that were first recognized through theoretical studies of how the most massive stars in our galaxy would evolve. And the prediction for stars that are roughly more massive, or start their lives with more mass than roughly 30 times the mass of the sun, is that these objects should end their lives as stellar mass black holes with mass on order of 10 times the mass of the sun. In contrast, and let me say that those stellar mass black holes start theory and have been confirmed observationally. So there's beautiful evidence that these things exist, originally from optical observations of binary stars, the orbits of stars around each other, one visible and one not, the black hole not being visible. And then today with the gravitational wave experiment of LIGO and Virgo, which has provided just beautiful confirmation that these stellar mass black holes exist. The story of the supermassive black holes are very different because they weren't anticipated from a theoretical perspective, but rather driven by observations. And it was observations of a small class of galaxies known as active galactic nuclei, or AGN for short. They're roughly 10% of all galaxies, and these galaxies exhibit a tremendous amount of energy or activity from their nuclei or their centers. So they're doing exactly what their name suggests. Their most prominent feature is this tremendous energy emitted from the center of the galaxy. And this is a picture that demonstrates this very beautifully. It's a picture at radio wavelengths where we see these jets of emission coming out, and you can measure very easily the kinematic energy in these jets. So it was supposed that something very powerful, some very strong central engine had to be powering these jets. And in addition to that, the emission right at the core was unlike anything emitted by stars or gas seen throughout the rest of the galaxy. So it was assumed that what we're seeing here is the hot gas just outside the event horizon that's falling into the black hole. In other words, you're seeing the accretion, mass accretion onto the black hole, and that's what's heating up this galaxy. So it's an observational and indirect case for the supermassive black holes. And this was made, this suggestion was made roughly half a century ago. And that led people to suggest that maybe all galaxies, even the quiet galaxies, have supermassive black holes at their center. In other words, the idea is that there's a single supermassive black hole at the center of every galaxy. So you can think of the center, and galaxies are flattened disk-like structures. And this is a galaxy that would look very much like our own if we could get back and get outside and look back at it. Our sun is about halfway out in a spiral arm structure. And the density of stars in these galaxies tends to get much higher towards the center of the galaxy. In fact, almost everything gets more concentrated, more extreme as you head toward the center of the galaxy. So you can think of the center of a galaxy like the urban cosmopolitan center, and we live out in the suburbs, but there's no unusually strong activity coming from the center like those active galactic nuclei. So the idea is that there's just a dearth of matter that can fall onto the black hole and power that energetic phenomena that we see in the subclass of galaxies known as the active galactic nuclei. So if we're going to explore this idea of the existence of supermassive black holes and the possibility that maybe all galaxies harbor these supermassive black holes, our galaxy is certainly the best place to look. The center of our galaxy is the closest center of a galaxy that we'll ever have to study. The next closest center of a galaxy is 100 times further away. So we have the opportunity to see far more detail at the center of the galaxy just due to its proximity, its closeness. Now, this is a picture taken on the Big Island of Hawaii. And it shows beautifully what the Milky Way looks like from our vantage point. So we are looking through this plane towards the center of the galaxy. The white band is all the starlight that comes from stars in our galaxy, and hence the name Milky Way. It's a Milky Way of stars. And you might notice not only that band of light, but also the dearth of light that comes from in the center of that band. There's an obscuration, and that obscuration comes from all the dust that's in our galaxy. So the dust in our galaxy is very much like smog in Los Angeles. So we Angelinos have a very good sense of what dust does. In fact, it's really the similar properties where a typical dust particle size might be up to about a micron. And dust is very good at blocking light that has a wavelength that's comparable or smaller, in particular smaller than the dust particle. So at optical wavelengths, what our eye detects, light has a very hard time, and in fact, it's basically a screen, can't make it to us. In fact, only actually technically 1 out of every 10 billion photons makes it, or light packets makes it from the center of the galaxy to us. If we go longward of what our eye detects to the near infrared, which is where all this work that I'm going to share with you has been done, in particular, most of it's been done at 2 microns. 1 out of every 10 photons makes it to us. So we can actually see and perceive the center of the galaxy. So you can see how this project was really born out of the advancements in infrared technology. So you really needed the infrared detectors to advance to a point to even consider doing this project. Now, to show that there's a lot of mass inside a small volume, the most direct way you can do this is to look gravitationally. And in the beginning, we use much, well, actually, let me just explain what this very simplistic diagram shows. So stars are going to orbit the center of the galaxy based on whatever is in the mass that's inside their orbit. So each star allows you to figure out what mass is inside its orbit. So if we want to show that there's a lot of mass inside a small volume, we're really inward bound. We want to be able to see the stars that are as close to the heart of the galaxy as possible, because those are the ones that are going to have the most constraining ability in terms of where that mass, confining that mass to a small volume. So you want to get as close to the center as you can possibly go. So that tells you why you want to get to high angular resolution to actually see these stars that orbit. Now, the initial conception of this project was not to see full orbits. And so while orbit seems so obvious and sort of direct proof today, it's not what we had in mind, because we didn't know what the masses were. We were just thinking about measuring the velocities or the speeds of stars, and the gravitational prediction is that the velocity should get faster as you go toward the center in a very specific way, as 1 over the square root of r. So you look for fast moving stars in close compared to far away. And in order to make that argument, you have to assume things about the distributions of stars and the orbits of stars. So there's still some underlying assumptions. If you can measure the individual stars, you get away from those assumptions. So this is a project that started with a simpler, although less direct objective. So I'll try to get into that distinction as we go along here. But that need to see stars that are as close to the center of the galaxy as possible tells you why Keck is really the key to this experiment, because the larger your telescope, the smaller the detail that you can see. So it scales as 1 over the diameter. The Keck telescope is a 10-meter telescope. It is the largest scientifically operational telescope of this size in the world. And it was a decade before its time, I mean, this was really amazing. And what was so, the reason it was so ahead of its time is that the primary mirror, which is how we describe the size of the mirror, instead of building one single mirror blank, it's composed of 36 hexagonal segments. Okay, so this was hugely controversial. So the fact that David Saxon was not only willing to back this from a financial point of view, it was really a technical risk, and yet has defined the way telescopes are built since that time. It's been so successful. So James Webb Space Telescope, which is about to be launched, uses this architecture, as have many of the next generation telescopes that I'll mention at the end of this talk. Okay, so let me just give, for those of you outside of astrophysics, just a brief sense of why would we put this telescope in Hawaii? I mean, we're California institutions building this. Why is Hawaii the place to go? And the reason is that you want to get to a place where you're looking through as little atmosphere as possible and as calm an airflow as possible. So we tend to put, and you also want it to be have low water content. So you go high, you look for high peaks. So on the Big Island, we're on the top of Mauna Kea, it's 14,000 feet. You're above most of the water vapor. So that solves one problem. And then to get smooth airflow, our atmospheric science colleagues will tell you that large bodies of water create smooth airflow. So you often find observatories on peaks, mountains that are near large bodies of water. So islands, so the Canary Islands, Hawaii, or the Andes, which has the peak, but smooth airflow from one direction. Okay, so we also don't like lights. We spend a lot of time trying to collect light from very faint things. So you want to be away from dense urban population. And this is an interesting, there's an interesting tension because you're trying to build some of the most advanced instrumentation and facilities, but you want to be away from urban centers. So that's Hawaii presents a very nice balance between dark sky and pretty ready access to both the high-tech industries as well as high-skilled labor. Okay, so Mauna Kea, there are telescopes from all around the world, or about a dozen of them, and the Keck telescopes are the two ones up here that look like tennis balls. They're huge. And also to give you a sense, I don't know if I've already said this, but 10 meters is like the width of a tennis court, to give you a sense of scale of that mirror. The technology that we use has also evolved a tremendous amount. We used to go to the summit, then it was possible to observe from the headquarters of Waimea. There's about a staff of about 100 people who work in Waimea. Now you can control it from UCLA. And due to COVID, now you can work from home. This is something that the observatory never wanted to let us do, but we're very thankful because we only got shut down by COVID for a few months. And then shortly thereafter, we were back online, able to take data. Now, the data that we take has already been mentioned. The first decade of this experiment used this very hardware simple but computationally complex technique of speckle imaging. So the idea here is that the atmosphere, which is great for us, it allows us to survive here on Earth, but it is an absolute headache for people studying the universe. And if you think about the light from the center of the galaxy, it's been traveling to us for 26,000 years. And in the last 30 microseconds, it hits the top of the atmosphere and gets distorted. And as I was sharing with some of our first year grad students, this pattern is actually an interference pattern of coherent cells in our atmosphere. So there's a large number of ways that you can analyze this, but the real work is in the post-processing. So developing techniques that allows you to extract what the underlying object looks like versus what the atmosphere has done to you. These are 5 bright stars. If there was no atmosphere, the size of the stars would be the smallest structures dancing around here. So one of the things that's wonderful about the Keck Observatory compared to maybe working at a national facility is that there's a real willingness to let astronomers come in and make changes. So to beat the atmosphere, you can get above it, which is the solution of a Hubble Space Telescope. Hubble is the diameter of Hubble Space Telescope is 2.4 meters. Keck is 4 times larger. And in fact, the kind of work that that we've done at the center of the galaxy, the benefit goes as the diameter to the 4th power. So it's a very strong gain. So roughly a factor of 100 if you can overcome the distorting effects. So all we did in the early days, it was a very simple change, which was to change the rate at which an existing instrument could read out, and then the scale of the instrument. So just optics and a little bit of electronics. And then all the work is really, as I said, in post-processing. Now, the next 10 years, we've, and we always knew this was coming, and in parallel to the speckle imaging, there was a lot of collaboration with Keck Observatory on developing these things, but this has really transformed what we can do. It's now hardware complex and software sort of simple. So here, the hardware, the idea is to introduce not what's called a deformable mirror that can counteract what the atmosphere has done to you. So it's not the primary mirror, which is segmented, but those segments are heavy. You can't move it around, and you need to be able to move around these segments on a time scale of 1,000 times a second. So the light is you re-image the primary mirror onto something that's more on order of a foot. With 360 actuators that can move in and out to counteract the distorting effects of the Earth's atmosphere. And in order to tell our deformable mirror how to move, we shine lasers up to a layer in the atmosphere. And this is just a fluke of nature, where there are sodium atoms from meteorites that are trapped there just because of the structure of the atmosphere. So we can shine our lasers and make an artificial star that we can then look at to move our deformable mirror. Okay. So this is what allows us to get to the diffraction limit. So if we would take a long exposure, we see those 5 bright stars that are just fuzzy blobs that's limited by the atmosphere. And now we're at, we can get to information that's at the diffraction limit. In other words, get to the theoretical limit of what the optics in the telescope set, as opposed to what the atmosphere is limiting you to. Okay. Oh, let me, okay. So these, where we think the black hole is in the center of this box. We actually take images over a larger region than even this. And we've, over the last 25 years, we tracked thousands and thousands of stars, all of which are important to track. But the ones I'm going to focus on in the next animation are the ones that are in the center of the box. So you can see that without the atmosphere, correcting for the atmosphere, you can't even see the individual stars. And it's these guys that we want to watch move. And as Fertila mentioned, the first proposal we submitted was turned down. They just didn't believe our technique would work. And the reason there was so much skepticism is that it was the first experiment that demanded that those segmented segments of the telescope be aligned so that you could get to the diffraction limit. In other words, you have to align those segments to a fraction of the wavelength that you're using. So that's technically very challenging. And this is the first experiment that really demanded that actually have successfully been achieved. But it was. And then there was question about whether or not we would see stars and whether or not we could see them move. So the next animation, I have to say, I could watch this animation all day. It's a fourth of the real estate of that little box. And when you're following it with images, which is all we could do for the first 10 years, you're trailed by a dashed line. And when spectroscopy, which allows you to measure the motion along the line of sight, in other words, the missing dimension, you're trailed by a solid line. So you can see that things appear and change. And that's all because the technology is changing, not because these individual stars are changing. And you can also see that the initial objective, which was a 3-year project just to measure the velocities, have gone way beyond what we originally thought. Okay. But let's keep that in mind. So you can also probably find my favorite star in the universe. Its name is SO2. It's my favorite star because it goes all the way around in 16 years. And we have both images and spectra that complete the orbit. And that allows us to do far more than just discover the black hole. So before this, as this project started, we knew that there was 4 million times the mass of the sun inside this enormous region depicted by the circle. And what this project has done through these various stages has to confine that mass to a volume that's a factor of 10 million times smaller to a region that corresponds to the size of our solar system. So if you think about our solar system, the mass is roughly 1 times the mass of the sun, all the mass is in the sun. And in this equivalent region, we have 4 million times the mass of the sun. And also to give you a sense of progress in terms of advancing the case for a supermassive black hole, not only at the center of the galaxy, but anywhere, that factor of 10 million, think about, I don't know, what would we like to get more of? If we think about like maybe the budget of UCLA or the budget of the physics department, if we could multiply it by a factor of 10 million, that's pretty good and would have amazing impact. And that's what's happened here in terms of our change in understanding of the possibility, or moving the possibility of a supermassive black hole from a possibility really to a certainty. This, is another way of thinking about it, or just showing this is the density of dark matter on the y-axis versus the mass of the black hole. In the beginning, people talked about clusters of dark objects explaining the mass that was seen inside that giant circle. So that first, just measuring velocities advanced us a factor of 1,000, making the lifetime of clusters of dark objects shorter than the age of the galaxy or the universe, which is actually shown with this green line. So once you're above the green line, clusters of dark objects are unlikely. But when we first started reporting this result, of course, as scientists, we're pretty good at coming up with other explanations. So the particle physicists came up with this notion of a fermion ball, which is like the equivalent of a neutron star, but rather than being made up of neutrons, one of the elemental components of the nucleus of an atom, you're now composed of fermions. So it's an even more compact object and denser. And now with the orbits, you can even rule out the idea of the fermion ball hypothesis. So, these alternative hypotheses also really drove us to keep going with this project. And once we got to velocities, it was also clear that the orbital scale was likely to be decades. And that was important because, of course, you can't do a project that's going to be much greater than a human lifetime. Take the sun. The sun takes 200 million years to go around the center of the galaxy. And here we have objects that go around on order of a decade. But that was not clear at the beginning of this project. One, you have to understand how close you are to the black hole and the mass of the black hole. So there was a real sea change, or an exciting moment, I would say, in roughly the year 2000, when we understood that we could go beyond just velocities and really get to orbits. And at that point, it was sort of interesting because two things were happening simultaneously. One, we were understanding that you could get to orbits just by waiting. In other words, this is an experiment where just patience rewards you. My joke is, it's like a fine wine, just gets better with time. But in addition to that, you're also simultaneously improving your technology. So at about the same time, the technology was also opening up. And for the first time, we could see or understand the stars themselves as astrophysical object, not just the canonical point particle under the influence of gravity. And what was so much fun at this point in this project was almost every prediction that could be made about what is expected to be observed in the vicinity of the black hole was inconsistent with observations. I like to say it's like job security or a kid in the candy shop. Like, there was so much to do on so many different astrophysical fronts. So in this animation, I'm sharing with you three mysteries that emerge from this stage, and it really is driving forward a lot of the work in terms of understanding this role, or this feedback role, that we think the black hole plays in controlling or regulating the formation and evolution of galaxies. So the stars are now color-coded to what kinds of stars they are. And I couldn't resist, because I'm teaching Astro 81, and we've just talked about all of this, to put in a slide that shows, well, how do you figure out what kind of stars they are? You take spectra. Most astronomers know that in a big, broad audience, you shouldn't show spectra, but I have to show spectra because they're so important. So the spectra are much harder to take from a telescope time perspective. You need to invest much more time, but I should also give a huge shout out to the instrument that we use, OSIRIS, which was built by our very own Professor James Larkin. So this was a really important instrument that was developed at UCLA and enables us to take these measurements fed by the adaptive optics system that allows us to understand the kinds of stars. And so each star, we can actually see the spectra. So it's breaking up the light into its as a function of wavelength. And you see these absorption lines that come from the quantum mechanical interaction between the atoms and stars. And that allows you to figure out the temperatures. And of course, we can put that together with models and say, infer what kind of stars they are. So without going into more of the astrophysics, I can infer that these things look like either young stars, and and on the scale of these things, young means a few million years, or old stars, which is a billion years. And the nice thing just to keep in mind about young stars, if you scale the lifetime of stars to a human lifetime, a young star is like the human gestation period. So these are really, really young, the early stages of these stars' lives. Okay, so you can through these spectroscopic observations, you can tell what kind of stars they are. And okay, so what are the predictions? Prediction number one, those young stars shouldn't be there. Young black holes introduce huge tidal forces. And in order for gas clouds to collapse to form a star, you need the cloud's self-gravity to overcome those tidal forces. And the density of the gas that we see at the center of the galaxy today is 10 to the 11 times too not enough to get star formation to happen in situ. So this is not just a little problem, this is a big problem. And in fact, for years, people argued that young stars at larger distances, that presence of things even further away was why we shouldn't believe that there's a supermassive black hole at the center of our own galaxy. So now the closest star, even my favorite star, SO2, we identify as a young star. So there's this thing that I like to refer to as a paradox of youth, and explaining how these young stars form in such an inhospitable environment drives a lot of the work that we do today. A second problem that is also intriguing is the old stars. So the old stars are color-coded orange. So as I said before, they're 1 billion years old. These stars, because they're old, they've been around for a long time, and they have enough time to gravitationally interact with the surrounding stars to migrate through what we call dynamical friction to be close to the center. In other words, the natural state is to expect there to be an enhancement of old stars around the supermassive black hole. And in fact, we use that expectation of that enhancement, which we call a cusp, as a way of looking for supermassive black holes in other galaxies. There's a dearth of them. So it's the opposite of what you expect from a dynamical perspective. So raising all sorts of questions. These two questions have driven a lot of work in terms of understanding both, how can you alter their appearance, or how can you alter the physical processes? So can you, in the case of the old stars, can you somehow alter their appearance such that they're actually there, but they don't have the characteristics that you would expect? And both of these problems have driven, like I say, a lot of different work or ideas from a wide variety of angles. My current favorite of the mysteries are the pink stars, the magenta stars. These are things that we didn't even think to make predictions for. We couldn't imagine that such objects would exist at the center of the galaxy. Okay, so these are objects where they look compact for most of their orbit, but then they come close to the black hole and they get tidally elongated. And you can actually see this stretching out. You can see it spatially resolved. They get tidal tails, and then they pass by the black hole and they become compact again. So again, it's amazing that we can make these measurements over time. And the reason this is so remarkable is that for these interactions to happen and for the object to survive, and yet for these interactions to still happen, these objects have to be 100 times larger than any star that we predicted to be in this environment. And one of my favorite ideas that we're working on with Professor Smadar Naos is the idea that pairs of stars, binary stars, can be driven to merge by the black hole. So this is a 3-body interaction. And when stars merge, they become bloated. They become incredibly large and therefore can interact with the black hole in this way. And the reason I'm so excited about this is not only because it may explain this phenomena, and it may give us a process that explains the other, some of the other two mysteries that I've just described, but it also may explain some of the mysteries that are seen with the gravitational wave experiment, LIGO and Virgo. So in that case, the gravitational wave case, the mysteries or the excitement there comes from mergers that are happening more frequently than predicted, one, and two, they're seeing stellar mass black holes that are larger than predicted. So the question is, are we uncovering a process, this three-body interaction that drives mergers by the central black hole, that it may explain the phenomena that's being seen with LIGO. So we're continuing to look at this and to understand this process in the context of the center of the galaxy, but to use it to explain perhaps what's going on elsewhere in the universe. All right, now just quickly, I want to end this talk with a different angle. So we've talked about what's driving the work right now from an astrophysical perspective. What drives the work today from a fundamental physics perspective is the idea that you can use these stars to test Einstein's theory of general relativity. And there's two fundamental tests that once we got to orbits, that immediately became obvious. I mean, it was an exciting moment, because not only did we understand that orbits were measurable and there was a lot more to come, but others started to write about these kinds of measurements that could be made. And the first one that was within reach was the idea of looking for the relativistic redshift, which is just looking at how gravity, so Einstein's theory of general relativity, which mixes space and time, should affect the photon. In other words, the photon loses energy as it has to climb out of the gravitational potential, and therefore spectroscopically, the velocity that you see has an extra shift due to this effect. So that happens to get a seat at the table to do this work. You have to make measurements of the orbit all the way around once, and then the next time it goes through closest approach, you have the ability to make the measurement, because you need to understand the shape of the orbit in order to test how gravity works. Okay, so that's the relativistic redshift, and that was beautifully confirmed in 2018. There was a 6-month period where the signal should have been was strong enough for you to see, but you had to have the earlier 20-odd year, 2 decades worth of measurements to combine with those key 6 months. So there was this extra signal, and that's the deviation here in terms of the velocity that you infer from the spectroscopy along the line of sight as a function of time. So you can see it take off. It follows what you expect from general relativity, which is the dashed line. Of course, what Newton predicts is the bottom here at 0. And all of this is, in fact, the biggest source of uncertainty is the knowledge of the orbit. So this is a test that's just going to get stronger and stronger as our constraints on the orbit get stronger. Okay, so what I'm finding particularly exciting is actually the second test. And the second test is looking at how the object itself moves through space-time, which is called the precession of the periapse. And the precession of the periapse, the prediction is that the orbit shouldn't come back to the top, but rather it should precess or rotate in a prograde direction. In other words, it overshoots and will make like a kid's spiral graph pattern. Okay, so this is exaggerated, but what we're seeing, and again, this is a signal that's going to that you need the whole orbit, but you need the comparison of the closest approach to the furthest approach. So we're sort of in early days. I would say this is early days. So I'll tell you why I'm interested, but also what worries me. So it's rotating in the opposite direction. So it's in a retrograde sense at twice the speed that you expect from relativity. And if you take this at face value and say, this is physics, what that says is what could create that effect is a distribution of dark matter. In other words, matter that doesn't emit light, and you see less of it when you're at closest approach and more of it enclosed at furthest approach. So it's a difference which causes the orbit to open up. And you can say exactly how much would be consistent with this measurement. Now, the thing that keeps me up at night, or the thing that you have to stop and ask, which is always the case when things don't work, how can this go wrong? And here you have to remember we're combining data for 25 years, and you have to put everything in a consistent reference frame. So what keeps me up at night is how do you compose a stable reference frame where with thousands of stars where everything is moving and moving under the influence of the thing that you're trying to study. So it's a non-trivial thing, and it's the thing that if you lift up the hood is the hardest piece to do. So early days, exciting, but not convincing yet. And I hope within the next, I don't know, 3 to 5 years, I'll have a more definitive answer, because this is a signal that just gets stronger as you head towards the furthest approach, which happens in 2026. So we have a few years to really not only work on making sure we have all our ducks in a line in terms of our methodology, but to collect more data. And of course, all of this gets better as you improve your technology. So today we use one laser to correct for the atmosphere. That actually only corrects 30% of the problem. Today we're we're designing and building an instrument with Keck Observatory that launches multiple lasers that basically does a CAT scan on the atmosphere. And that's critical because the height of that sodium layer is actually quite close. So the sodium star is coming down in a cone and your starlight is coming down in a cylinder. So there's some piece that you miss. And the larger the telescope is, the more you miss. So if you want to get to the next generation of technology or telescope technology, such as the 30-meter telescope, so this is a $3 billion project that's a collaboration between UC, Caltech, Canada, Japan, China, and India. It is a fascinating project, not only from a technology point of view, but a political point of view. But this multiple laser system is a critical risk mitigation for this future technology. And of course, what we'll do today is we'll improve our ability to see the center of the galaxy with today's telescope, and dramatically improve with a 30-meter telescope, because today we only see the tip of the iceberg. Most stars are fainter than the distribution of stars increases as you go to fainter stars. So you're dominated by the faint stars, which means things just blur together. Today, we can't see a typical star like the sun at the center of the galaxy. So one concern with all these oddities that we see is that they're odd because you're just seeing the weirdos at the top. It would be, the analogy I like to make is it would be like trying to understand the financial market by only looking at the largest transactions. When in fact, a huge amount of our economy is driven by the smaller scale interactions. Okay, so I'm excited about the next generation at Keck and going beyond. But I do, before I end, want to really call out the wonderful collaboration that has gone into making this a success. For the last 2 decades, I've had the just extreme pleasure of working with Mark Morris and Eric Becklin. It is absolutely an example of the whole being greater than the sum of the parts, with each of us bringing our own expertise and experience to this project. Also in this picture is my first grad student, Beth Klein. Today, the core collaboration has grown a lot. We're about 30 people. And the core collaboration means the people who are responsible for the collection and analysis and development of methodologies to do the science. We have a broader network of collaborations that's about 100 around the world. Lots of students have come out of this, have done all sorts of jobs, including academia, but also going into the military, going into the financial industry, looking at big data analytics. There's been a wide variety of career paths coming out of this group. And I have to end by really acknowledging the tremendous support that we've had from UCLA and the National Science Foundation as our backbone. And then foundations who will focus on early career, the Sloan Foundation, the Packard Foundation, and the MacArthur Foundation. And then the more recent funding that have allowed us to expand and move on from the Heising-Simons, the Keck Foundation, and the Moore Foundation. And then this just amazing group of UCLA donors led by Arthur Levine, and also where Howard Preston and others have made just a huge impact on our ability to go forward with this work. So thank you for your attention. it's just been an amazing ride that I'm hoping will give, another 2 decades worth of science.
Wow, thank you, Andrea. If people want to hit the reactions, there's an applause under the reactions. And we'll see them under the participants. Or you can unmute and applaud. It's just so inspiring to see.
I also just want to actually, thanks, David. I want to just say one more thing because I think Ali Pache is here because Roberto was the chair when I was first hired with Mark, and Ferd brought this up with Roberto. And the interesting lunch was relayed. But I do want to say that since that time, Roberto, I was just incredibly supportive. I've had a very, very, just the good fortune to work in a department where the senior members have provided the support and the advice that's necessary to make a really large scale project that has had the truly big ambitions succeed.
Here. So we have time. We'll do is we do a little formal question and answer first, and then people are welcome to hang around for the virtual wine and cheese after we turn off the recording. But for the first few questions, we'll keep the recording on. And what I would like to do with a lot of people here, we'll do the raise hand feature. But I would love it if we could start with the students. If any of the students have any questions about the work and the history and the science that's coming, let's first give the students a chance to raise their hands. Don't be shy.
Yeah, I was wondering if you could give a little overview of how adaptive optics work.
I don't remember exactly.
Sure. So this is a question on how does adaptive optics work? And in fact, let me just also comment that even the story of adaptive optics itself is interesting. So adaptive optics is this hardware approach to solving the problem of the distortions of the Earth's atmosphere. And it was being developed in astronomy for a long time. So from the time I was a grad student, there were projects aiming at the development of this technology. But it turns out there's other industries that also care about looking up and down through the Earth's atmosphere. In particular, the military cares about this. Astronomy and astrophysics community did. So there was an interesting moment in the early 90s when this technology was declassified because the government didn't want to keep giving the astronomers money to develop what was already known. So this technology, let's see, so we have a deformable mirror and I was actually just thinking maybe I can show you a quick, actually I'm not going to try it because I will never succeed in finding this animation. So the key is this deformable mirror. And the deformable mirror has segments that that are going to move in conjugate to what the atmosphere does. So if you think about the atmosphere applying distortion on your wavefront, you can think of it as a circus funhouse mirror that distorts how things look. And the job of the deformable mirror is to have the opposite shape to what the atmosphere has done, so that things look flat after going through both the atmosphere and the deformable mirror. So 2 bounces that straighten things out again. You have to keep up with the atmosphere, and the atmosphere changes at 2 microns at about 1,000 times a second. So this deformable mirror has to take on that opposite shape really quickly. And so it uses little piezoelectric motors to keep up with the atmosphere. Let's see. So we have the deformable mirror. That's the one key element. And then the other key element is, what do you look at to understand how the atmosphere has affected your wavefront? So to do that, you need to look at something very bright. So either you can look at a natural star, which was the starting point, some star that's bright enough that if you image it at 1,000 times a second, you can see these distortions. But only 1% of the sky has a a bright star close enough that that you can do this trick. So that was the early way. The center of the galaxy doesn't have such a star that you can use. So where this technology really took off in terms of being really powerful for the field of astronomy and astrophysics is with this idea of the laser. So where you you stimulate the sodium atoms in this thin layer of the atmosphere to shine like a star, and you image that to tell you how to move your deformable mirror. So there's a separate system that's looking at your bright star, your guide star. So Cody, I hope that's a little bit more of an introduction to adaptive optics. It's an amazing technology. I mean, there's computational challenges there. So your computer speed, you need to computationally be able to keep up. And with the 30-meter telescope, this is going to be even harder because you have more segments that you have to keep up with. So just even the computational challenge is non-negligible. Do you have the computing speed to keep up, both with the number of actuators and the timescales? And all of this gets harder as you go to shorter wavelengths.
Thank you so much.
Andrea is the world's biggest fan of adaptive optics. We had a graduate student, Sammy Kamas, had a question. Sammy, do you want to say it's in the chat, but why don't you say your question out loud?
Sure. Great talk, Andrea. I loved it. I love hearing you talk about black holes. It's awesome. So I was wondering, like, what type of dark matter, like what theory is most supported by the data? I know it's early, but
yeah, I mean, you have to ask, like, is it even reasonable to talk about this amount of dark matter and what form would it take? So we have, the way to think about it is we have on order of 20, if you interpret this as a physical reality, 20,000 times the mass of the sun inside SO2's furthest approach, which is about 0.01 parsecs. If you think about parsecs, if you don't like parsecs, multiply parsecs by 3 and you get light years. And one of the interesting things about this is, remember the cusp that was missing from that we've talked about, the dearth of old stars? If you just think about maybe how much mass should be in that cusp, it's roughly this order. So it could be the missing cusp. So that would be interesting. And then the alternative explanation is it could be particles. It's quite unlikely that this is particles. It's hard, but that depends on what kind of particles you might reside at the center of the galaxy. And what you might think about here is the leftover particles from the early formation of the galaxy. So the galaxy forms out of the background goop. And there's some density fluctuation in the primordial dark matter that gives rise to presumably the black hole and the galaxy. So could this be the that dark matter that should also be concentrated at the center of the galaxy? The other way that people might be interested, that we think about dark matter, and Professor Tuan Do has thought quite a bit about this as well. Oh, sorry, I should have mentioned Tuan. I can't believe I didn't mention it. So Tuan Do and Jessica Liu are two other
Did you need to help everything?
Yeah, I did.
collaborators.
Again, terrible concentration already.
Well done. Yeah.
But we need someone
similar to what you said, Tor.
So dark matter, if it's there, could also permeate stars. So what would dark matter infused stars look like? Like, do you change the actual appearance of stars? So could some of the young stars that are most tightly bound, or could some of the stars that we think are young that are most tightly bound, like SO2, simply be brighter because of this infusion with dark matter? So Professor Do has thought quite a bit about that alternative.
I'm just going to ask one question out of sequence, just because one of them was kind of brief. So Jessica Asharte, do you want to ask your question out loud? And then we'll move on to Randall after you.
Sure, thank you. So I was just wondering if you've used any space telescopes in your research so far, and if you're planning on using the James Webb later on.
So we do use already Hubble Space Telescope, and it allows us to get the larger scale picture of what's going on at the center of the galaxy. But because the density of stars goes up as you go to the center, you're just much better off with Keck. So we use it for the larger context. The team has put in a bunch of proposals to use JWST, James Webb. So it's a 6-meter class telescope. So again, it's a great thing to get the larger, broader context that we can interpret what we're seeing with the Keck. So we use the Keck to really drive what we can measure dynamically, the things that allow us to get to orbits, and then just the bigger picture that you might need to interpret, especially the astrophysical part, comes from Hubble Space Telescope and James Webb.
Great, thank you.
I was told that Manasa had her hand written up, but
Oh yeah, she wrote it. She wrote it. Manasa, you want to ask your question?
And then we'll go back. Sorry, Randall. Then we'll go back.
Oh yeah, of course. My question was about like the differences between where we've seen supermassive and stellar massive black holes. As you talked in the beginning of your lecture, you were talking about the differences between those, and I was wondering like where would like stellar massive black holes, like where have they been observed? Are they like just inside certain galaxies, just like in certain parts, or are they outside of them on their own, or?
So thanks, Manasa. Manasa is a student in Astro 81, so one of our undergrads. So I love, Manasa, that you asked a question. So the stellar mass black holes come from the most massive stars in our galaxy, and you see massive stars throughout our galaxy. So you expect these stellar mass black holes to be everywhere in the galaxy. In the same way, when you get towards the center, that you should expect things to concentrate, you might expect an entourage of stellar mass black holes around the supermassive black hole. So another form of dark matter could be just these stellar mass black holes. You get that concentration. And one possible way, if this if this signal really is real, that one might think about disentangling this, is that things like stellar mass black holes, if that's really the source of them, you should be able to see gravitational lensing events from the thousands of stars that we're observing around the black hole. In other words, in order for there to be enough of them to explain this mass, you should see those lensing events. And this is something that this next generation AO system, adaptive optics system, should help us find. So one of the many ways that one might think about disentangling this potential question.
Okay, we have like 3 others. If you're okay, Andrea, 3 more students have questions. Can we?
Oh yeah.
Are you game for that? Okay, Randy, and I'm going to read it out loud because his microphone is not working. It's in the chat, but I'll read it out loud. In the solar system, the planets all orbit in the same plane. But in your animation of stars orbiting the central black hole, they orbit in many different planes. Can you expand on the similarities and differences between these 2 scenarios?
Oh, I would love to. And in fact, I might just go back to that, share it, because it's the orbits are providing a very important clue, in particular for the young stars. So if we think about just the young stars for a second, out at some distance, if you watch this animation, and this is a 3-dimensional animation, actually, where we collaborated with the University of Illinois' Advanced Visualization Lab to do this. And at some point, you might notice that some of the young stars, color-coded as this aqua, so blue-green color, share a similar orbit. So in fact, roughly 20% of the stars in this region do form a plane very much like the planets in our solar system. So they go around in the same direction, and they're confined to a relatively thin plane. So taking that at face value, one of the ideas is that perhaps in the recent past, our galaxy had a thick accretion disk where the densities would be high enough to give rise to the densities necessary for self-gravity to overcome the tidal forces and collapse. somewhat like we think about the formation of Jupiters in our own solar system that might have come from gravitational collapse in an accretion disk. So there's an interesting connection between the dynamics in the galactic center and the dynamics in planetary systems. And in fact, if you think about the mass ratio between planets and their host star and the central star, that's very similar to the ratio of these massive stars that are the young stars and the supermassive black hole. So in fact, folks like Smadar, that makes it easy to go back and forth between these two very different settings where the same physical processes might be taking place. So there's a lot of collaboration right now with the exoplanet community and the galactic center community, because they're one of the few places where you can actually measure orbital dynamics. I think, hopefully I answered that question. So that there is some similarity in the orbits, which is an important clue.
And we can follow, if they have more questions, detailed questions, they can take for the wine and cheese. Henry Wong with the question I never thought of, and it's really interesting. Henry, do you have a microphone, and would you?
Hi, hello. Yeah, hi, Andrea. Good talk. Yeah, good talk. Yeah, you mentioned you guys use the actuating mirror to cancel the distortion. That got me thinking, like, what if I'm not looking at visible regimes, looking at like radio or microwave or even X-ray, then I could just use a phase array antenna. Could it be done?
So in fact, there's a beautiful experiment called the Event Horizon Telescope. So that's taking radio wavelengths and that are all around the world and trying to image what's known as the photon ring around our galactic center. What's already been published is the case of M87, so a nearby galaxy with a supermassive black hole. It's about 10 times more massive than our own galaxy. Turns out that our galactic center is much more difficult. So while we might think ordinarily that closer is better, what makes it more difficult from an imaging perspective, this multiple antenna from all over the world, is that you need the object to not change on a time scale of the rotation of the Earth. And the dynamical time scales for things right outside the event horizon scale with the mass. So M87, which is a more massive black hole, changes more slowly. So it doesn't change on a time scale of the Earth's rotation. In contrast, the center of our galaxy, which is a smaller black hole, changes very rapidly. So it's a much harder imaging problem. So rumor has it that they're going to release something quite soon, but it'll be super interesting to see what those guys get from studying photons that come from gas. So at radio wavelengths, you're mostly seeing the gas, and you're looking for how the gravitational field is affecting light from the gas behind the black hole.
Okay. Yeah, thank you.
Awesome. We'll just do two last questions. We got two last ones queued up, and then we'll do the wine and cheese. Okay. And so, Antoinette, would you like to ask your question?
Sure. Yeah, I'll just read it. Okay, so can one of the weird objects closely orbiting the galactic black hole, besides you mentioned like TL and the elongating ones, can one of those weird objects be a stellar black hole?
Oh yeah, so this is an idea that Mark Morris suggested a long time ago, the idea that these things might be what's called Thorne-Zitkoff objects. So they're stellar mass black holes that are accreting gas from the surrounding region. So you're seeing something that looks like a star because it's a black hole basically with an atmosphere. So one of the many intriguing ideas that have been put forward to explain the things that we see.
Nice. Thank you.
And I think this will be the last one, unless no one else in their hand said, looks like we got everybody before they came. This one's going to be fun. Paul Hamilton's children have a question for you.
So like the magenta stars in your presentation, you said they were like made up of other stars. Are they bigger than the blue hypergiants? Because like those are really big.
Yeah, they're bigger than even the red giants.
Are
So
they made of like
they might be a merger of two red giants. I mean, that's a way to get something even bigger. But basically, when you merge stars, it's almost like resetting the clock. They become like super baby stars, even younger than at stages even younger than the ones that we see that are a million. They're just huge. And stars in the process of formation shrink. So when they merge, it's almost like resetting the clock. They become these huge fluffy things.
Thank you.
You're welcome. Thanks for the question. I love it.
I think we're going to thank Andrea one more time and end the formal part of this, but